so we're going to do just the paper, the question threes today, right, which involves planning and designing. All right, so before we look at any of the questions, let's just look at what the planning and designing incorporates. So the different sections of planning and designing are these 8 steps, are 8 different categories. We have the problem statement, right? And the problem statement is what is generally given of the problem that you want, that is there, and you need to design an experiment to solve that problem. Right? And then we have the hypothesis. The hypothesis in your exam sometimes will be given, or you will have to write an hypothesis, which is based on the problem, right? So based on the problem, you write a statement that you think is the reason for that problem. All right, so the statement can be a true statement or it can be a false statement. And then our aim sometimes is given as well, which is just basically telling us what we're going to do for the experiment, and it's based on your hypothesis, right? So it's either to determine, to find, or to investigate, right? From our last session, we had those 3 types of how we start our aim. And then our apparatus or materials are the things that will be needed to carry out the experiment. And your method would be written in present tense because you're giving instructions of how you should carry out the experiment. Your variables, you're manipulating, you're responding, or your control variable. Your manipulating is also known as your independent variable because these are the things that you're changing when you're doing your experiment. And then your responding variable, which is dependent on when you change what you're changing, what would you expect to happen. So your responding is basically what you are going to observe. And then your control variables, these variables are normally never one variable present. All right, so these are the things we remain constant, and there's always more than one when you do an experiment. All right, so if you're getting the volume of a specific substance the same, or the concentration, or the mass, whatever it is, those things will have to be listed under control variable. Your expected result would be based on your responding variable. What would you expect if someone's supposed to carry out this experiment that you design? What would they expect to get as their results? Right now, the expected results have to be a true statement. So you have to have resources or documents that would prove that your expected result is actually a true statement. Right? And then finally, your precautions, source of error, or assumptions. Now, your precautions are the steps to take to ensure that you minimize any errors that would be experienced. Your source of errors would be things that will normally happen when you do the experiments that will cause you not to get a true reading in your values. And then assumption, which is the hardest one, is basically you're saying that you expect this to be this, but in reality, it can actually change. So let's look at an example. So let's look at table salt. If you want to do an experiment with table salt, right, and you have the table salt present, and let's say you're doing solubility of table salts at different temperature. Now, an assumption could be that your table salt that is present is of the same makeup, meaning that it's only that concentration of salt that is present in your container, right? That's an assumption. But in reality, it can be that you use different brands of table salt in your container. So you have a container that probably use 3 different types of table salt that will change the concentration. Their concentration will differ slightly. So an assumption would be that because you have the container of table salt, so you're assuming that all particles in that table salt is of the same concentration. All right, so is this clear for everyone, these steps?
Yes, sir.
All right, so all planning and designing experiments contain the specific areas. And then for your exam, some questions will normally add this part, which is your discussion. All right, and discussion basically tells us, based on your expected result, what information do you have to actually explain that what you expect to happen will actually happen. All right, so let's use this knowledge now to answer our question 3. Now, before we move to the questions, the first thing to note about these questions is that you have to understand which topic the problem is actually under, right? So it's not to read and say, all right, let's look at this one. So it says you are provided with the following reagents. We have 0.1 mole per dm cube of magnesium sulfate, copper 2 sulfate, and iron 2 sulfate. The equal lengths of metal strips labeled X, Y, and Z are believed to be magnesium, copper, and iron. You are required to design an experiment to identify metals X, Y, and Z. The A-man hypothesis is given. All right, so for this one, it's easy because your A-man hypothesis actually tells you which topic it's based. But let's ignore that there was no A-more hypothesis here, right? How would we know which topic this problem is based on? Anyone wants to try that? So we're looking at the aim. Go ahead.
Based on the hypothesis.
All right, so without looking at the hypothesis or the aim, all right, so let's say the question was actually just that part. So we weren't provided with the aim or the hypothesis. How would you know which topic it would be under? All right, so as I say, in reactivity series of metals. All right, so yes, that's the topic, but how would you know that that's the topic that this experiment would be based on?
Because of the metal strips.
All right, so we have the metal strips, right? And if we have the metal strips and then you have different solutions, then if you mix them, then that's a metal reacting with a solution. So therefore, that is basically telling us that it's a reactivity series. All right. So before we look at any of these, let's just look at the topic of reactivity series before, because once you identify the topic, the next part is you need to jot down what you know about the reactivity series. All right, so let's go. What do you know about the reactivity series?
Metals are placed in order of their reactivity.
So they are placed in order of their reactivity. All right, great. So do we know that order that it's placed in?
Yeah.
All right, so let's go. The order, starting from the
Potassium.
From the highest or the most. So that is potassium. Then we have, yes, go ahead.
Sodium.
Sodium, Na. Then
Magnesium.
Magnesium.
Aluminum.
Aluminum.
Zinc.
Zinc.
Iron.
Iron, which is Fe.
Lead.
Lead, which is Pp.
Hydrogen.
Hydrogen.
Copper.
Copper. All right, so we can stop here. Because we're stopping here because now we have all three metals that the problem is based on. All right, so we have the metal of magnesium, and we have copper and iron. So we have iron here, and then we have copper down here. All right, so what do we know about arranging these metals in this specific order? Anyone? What's the importance of arranging them like this?
They are less reactive as you go down the series.
All right, so yes, but if you're explaining that to someone that's just learning chemistry, how would you tell them, all right, so it's arranged in this order, so it's arranged in this order because,
I don't know.
anyone? Why you think it's arranged in this order rather than just being that the top ones are reactive, the bottom ones are least reactive?
Oh, it's probably moving from group 1 to like further down. I don't know.
Not really. All right, let's look at an example, just one that's not here. So let's take a chemical reaction, right? That involves, let's say, aluminum metal, and it's going to react with, let's say, sodium hydroxide. Would this be a possible reaction that will occur?
No.
Why would you say that?
It can't aluminum can displace sodium. It's higher up in the series.
All right, so now let's put that in a sentence form to say why we arrange these metals in this order.
Because the ones higher up can display.
Go again. Anyone?
The metals, all right, going from the top to the bottom of the group, the highest ones are able to displace the ones below them.
All right, great. So that's the purpose of your series, right? To show which metal can displace which metal in a reaction, right? So the ones below will not be able to discharge or displace the one above it. And that's because the one below is least reactive than the ones above, right? So this type of series, it only works best, well, it only works with the type of reaction known as a single displacement reaction, right? And the reason why it's a single displacement reaction is because we have a metal that is being reacted with a compound, right? So that's the reason why it only works in this order, right? So single displacement reaction. Thanks, Isaiah. Right? So it don't work if it's a double displacement because each metals from each compound will just switch places regardless of where they are in the reactivity series. All right, so let's look now at the metals that this experiment is focusing on. So it's focusing on magnesium, iron, and copper. All right, so we see that magnesium is the highest in this reactivity. So that means it will displace iron and copper, right? And then we see that iron will only displace which metal?
Lead, hydrogen, copper, silver.
Well, based on the three that we're looking at.
Copper.
So it only will displace copper and it will not displace magnesium. All right, and then copper, what would copper do? Would copper be able to displace any of the metals there?
No.
No. So therefore, if we notice the reagents that we're using magnesium sulfate, copper sulfate, and iron sulfate. Right? So we're just, before we even look at the questions that they're asking, right? Now, so let's put the formulas here. So this one is magnesium sulfate, MgSO4. This one is copper 2 sulfate, so it's copper SO4. And this one is iron 2 sulfate, it's FSO4. So therefore, if we react magnesium with these three, what will happen? Let's go to the top one. If we react magnesium with this, what will happen?
I'll stay the same.
It will stay the same, right? And then, so therefore it stays the same. And why would we say that it stays the same?
Because magnesium can displace magnesium.
What's that?
It's the same metal.
It's the same metal, right? So even if the magnesium displaces the magnesium from the compound, is the same metal, so you're still going to get the same thing. So the same thing will happen, right? Then this one. So do we have a reaction here?
Yes.
Yes, right, because magnesium can displace the copper here. So there would be a reaction. And then for magnesium and iron, it would be a reaction as well. All right, so we have for magnesium. Now let's look at if we use iron with these reactions. So if iron was to be able to react with magnesium sulfate, would we have a reaction there?
Yeah. The iron would, the magnesium would replace the iron.
Would we have a reaction?
No.
Yeah.
No, right? Because the iron is below magnesium, so it would not be able to displace it. So no reaction. All right, let's look at iron and copper sulfate. Would we have a reaction here?
Yeah.
Yes, we have a reaction. And then finally, it's iron and iron SO4. Same thing again, we have both irons present, so therefore we get the same thing. All right, and finally, we look at copper. So if copper reacts with MgSO4, we notice copper is at the bottom here, so that means all reactions with copper would be a no reaction, correct? So are we clear so far?
Yes.
All right, so let's look at the question now. All right, so the question gives us the aim, which is to identify the metals X, Y, and Z based on their displacement reactions. And our hypothesis says that a metal higher in the reactivity series will displace a metal lower than itself in the reactivity series from a solution of its salt. Your answer should include the following: the procedure. All right, so now we need to write a procedure that will tell us how would we able to prove that X is this metal, Y is this metal, and Z is this metal. All right, so all we did here, we're just going to put it in words now. All right, so let's go. Step one. What would we have for step one?
Gather materials.
All right, so gather materials. All right, let's write it. Not necessary that you write this one, but okay. So gather materials. All right. We're still going to continue at step one. So
And then
when you gather the materials, what would we do? All right, let's put it up so you can see. After we gather the materials, what would we do with these materials?
place place another metal into one of the solution and observe. I don't know.
Well, you're kind of on the right track. So let's fix that up so we can have it here. All right, so what we're going to do is that since we're using 3 reagents, all right, we're going to have 3 beakers of the same amount of these reagents. So let's write that in. So gather materials for, let's use 50 cm cube, even though this is a lot. So 50 cm cube of, I'm going to go with copper sulfate, iron sulfate, and magnesium sulfate in 3 different beakers. That's our first step. So we gather the materials, we pour this amount of copper 2 sulfate, iron, and magnesium sulfate in 3 different beakers. All right, and then you said that we're going to so we're going to place sample X in each beaker and observe. What do we observe here? Because you can't just say observe, you have to tell your reader what they should observe. What do you think we would observe in this case?
The reaction.
The reaction. So how would you know the reaction though? All right, as I said, color change, great. So you know if there is a reaction if you have a color change or you see something happening inside the beaker. So not just, if you say observe the reaction, then let's say the table actually shakes a little and the person see the liquid moving, they will think that that's a reaction, right? So you have to tell them exactly. So in this case, if we have a reaction, then the color will change. So we're going to use observe color change. All right. So the important or the best part of the procedure is that once you do it for one, you can just state that for the next procedure, we're going to repeat step 2 for metal X, Y, and Z. All right, so we don't have to keep on writing that place, sample Y in this, and then observe. Right, you just said repeat it for these metals. Right, so notice that this is just for one of the reagents. This is just for, all right, great, Isaiah. All right, so we say repeat steps 2 for metals X and Y. All right, then Isaiah added in different beakers. All right, so before we missed something here in step 2, let's add it right. All right, so it's not just step 2 we're repeating, we're going to repeat step 1 and 2 as well. Because step 2 would have X going in the 3 different beakers that we had there. Then when you repeat it for Y, it's going to be 3 different beakers again, and then for Z, it's 3 different beakers. So it's repeat steps 1 and 2. So steps 1 and 2. And that's our method there. All right, so the methods are normally not long, right? And they should be precise to the point of what you want to be done. All right, now let's look at the apparatus or materials, which is, this part is simple because what we're doing is just taking out what's there in our method and put it in our list right here. So we know that we need our reagents, right? So we're going to need our reagents. So let's write those. So we have the copper sulfate, we have the magnesium sulfate, and we have the iron sulfate. So we need those. We need beakers. All right, so the important part is you're not going to be graded down if you don't state the amount of beakers that you need. All right, so you don't have to state that you need 9 beakers, even though that's the amount that we need. You can just write beakers. All right, and also you need your samples of X and Y. So you need your X sample, your Y sample, and your Z samples. All right, and also you need a measuring cylinder. Why do we need a measuring cylinder?
To measure the amount of solution we're using.
Exactly. So in order to measure that 50 cm cube of your reagents, you need the measuring cylinder. All right, so Isaiah is saying here that we need a pipette. Well, not a pipette for this case, right? The measuring cylinder will do perfect, right? So we only use pipette for titration, right? So once it's any other experiment to measure the volume of a liquid, we just use the measuring cylinder. All right, so those are the things that we need for your experiment, and then 3 control variables. All right, so I just told you what are control variables. Let's go. What are 3 variables that will be the same when we are doing this experiment?
The amount of solution.
All right, so the volume of each reagent, right? Because remember we said we're using 50 cm cube each time. So volume of reagent.
Volume of product formed.
Volume of product formed. No, that's not a control variable because remember, some of the reactions will not produce a product. All right, so that means some reactants produce products, some don't produce products. All right, so Isaiah says it's the size of the strips, great. So the size of your metal strips, so that's important. And the temperature. Temperature. We could say temperature, right? But because we didn't mention temperature in our experiment, the other one that's keen is that's the one given in your problem. It gives you the concentration of your reagents. So we're keeping the volume of your reagents constant, but we're also keeping, so the last one here is the concentration of your reagents. So each reagent has the same concentration of 0.1 mole per dm cube. So these are the three control variables that we use. Right, so because we did not state anything about the temperature in our experiment, then it would not be wise to actually state that the experiment control variable will be temperature. All right, so format for your table of results. So how do we represent this results in a table? All right, so remember we have our reagents and then we have our metals. All right, so we can have the first column here to be that this column represents our reagents. All right, then we have the observation for metal X, the observation, and then all right, so we have the observation section, and this observation section can now be grouped into three different sections because we have three different metals. Right, so we have our Z column, Y column, and our X column. All right, we can put in our reagents because we know what they are. We can put in copper sulfate, iron sulfate, and magnesium sulfate. All right, so this table will do great with the observations, because each time you do the experiment, you just write what you'd observe in each of those sections, depending on the reagents. All right, and then finally is our discussion of results in relation to your aim and hypothesis. All right, so remember, aim was that about the reactivity series. All right, so how can we discuss what would be in our discussion here? It's 2 marks, so we don't have to write extreme a lot of things here. All right, so in this case, all we'd write is basically what we did over here. All right, so you can either write our equations that we did, so like these equations with magnesium sulfate and magnesium, the iron one and the copper ones. If we write all those equations here and show that at each point, which one will get a reaction and no reaction, and then you state that because of the reactivity series, the ones below magnesium, which is iron and copper, will not be able to displace magnesium, but magnesium will be able to displace it. Iron will not be able to displace magnesium, but it can displace copper, and copper will not be able to displace iron and magnesium because of the order of your reactivity series. So that's all that you'd say for your discussion. All right, is that clear?
Yes, sir.
Yeah.
All right, so you see how easy it is actually when you not just go towards answering the question, but actually just jot down everything that you know before, right? Because everything that we did here is actually the same thing that we just rewrite in our answers here. All right, so that makes it a little bit easier. All right, let's look at, yes?
Could metal and its metal ores come on question 3?
Metals and its metal ores. All right, so That's two-part. Metals can. Metal ores, no.
Thank Jesus.
Metal ores, no, because but what can come would be a metal. I think one of the questions have it here, so when we reach there, we'll see. All right, so let's look at January 2016. All right, so we have a lot of reading here. So Clean and Special Ways are two liquid laundry detergents manufactured by the same company, which may have been bottled incorrectly. So the Clean is known to be a soap detergent, and the Special Ways is known to be a soapless detergent. You are provided with samples of the two laundry detergents and have available to you the following reagents. Plan, design, and experiment to determine whether these two detergents have been bottled incorrectly. The aim has been provided for you. All right, so before we look at the aim again, all right, looking just at the problem, how would we know which topic area this is under? Yes, anyone? All right, so Isaiah says preparation of soap. Preparation of soap. All right, so I'm not asking the topic that it's in. I'm just asking, based on your problem, what thing in the problem would determine which topic it is. But it's not actually preparation of soap. Hardness of water. No, nothing in this problem that says hardness of water. But it's under that specific area, but how would you know it is that area? What's the key thing in this problem to tell you what the topic is? Key things are soap and soapless detergents. Right? Which comes under the hardness of water as what Isaiah actually identified before. So without looking at your aim at this, if it was not given, only this up here was given, then we know that it will be under the topic of that involves soapless and soap detergents. Right? And then when you look at your aim, it says to distinguish between soap and soapless detergents using the method of ionic precipitation. Right? So if the aim was not given, then those terms here in your problem will tell you what the topic is that the problem is under. All right, so what do we know about soap and soapless detergents? Anyone? What do you know about soap?
Chemistry.
Yes, so it's under section of organic chemistry, yes. But what do we know about soap and soapless detergent? Because if we don't know anything about it, then we're not able to answer this question here. All right, so let's think about, because we use detergents at home. Which one do you think we use mostly? The soapless or soap?
Soap.
So why would you say you use a lot of soap detergents?
Foamy, I don't know.
It's foamy. Yes, that is a part of it. Right? So for soap, it produces foam, right? It produces foam when we mix it with
Water.
when we mix with water. Right? So if soap is when it has a foam when mixed with water, then we can safely conclude that soapless would mean that when it mixed with water, there is
no foam.
no foam. Right? So now we're seeing a little thing here because if we notice, we have distilled water here, right? And we have mixed with water here. So we have one way how we can distinguish which one is which. Right? Anything else that we know?
No.
No, nothing more. All right, let's give you one more. All right, so all right, Isaiah brought up the fact about hard and soft water. What makes water hard? What makes it soft?
Ions present in the water.
The ions present in the water. The two main ions that are present in water to make it hard are which two ions?
Calcium and magnesium.
Great, so calcium and magnesium, right? Now, if we notice in our reagents that are provided, we have two calcium compounds and we have a magnesium compound here, right? So that means if we react, so that means for our soap, if we react our calcium carbonate with the soap, what do you think, would it produce a foam?
No. Wait. Yes.
Yes. All right, so yes, it will. And then this would be no. All right, the same thing will apply if it was calcium chloride or zinc or magnesium sulfate, right? So these are the things that we know. And just to note that our soap detergents, these are the ones that are created from fats, oils, right? And then our soapless detergents are ones created from residue of petroleum, right? So residue of petroleum produces most of our soapless detergents. All right, so now let's look at our questions. What's a hypothesis that we can use for this here? So remember, hypothesis and aim, they link very close. So they give us the aim. All right, so we're distinguishing between soap and soapless detergents using the method of ionic precipitation. So what could be a hypothesis that we could use here?
To distinguish between soap and soapless detergent. The aim. I don't know.
All right, so no. All right, so with your hypothesis, you have to be specific, right? So we know we're distinguishing between soap and soapless detergent. But what makes, so remember, hypothesis is what you think is the cause of the problem, right? Now your soapless detergent, so let's go with soap detergent. So you're going to say that our soap detergent,
Lathers more.
yes, or put it in small words, produce it. So it produces foam with reaction with water. And we're just going to use water as a simple one. While the soapless does not, right? Because the foam is your precipitate of your reaction. So this is a method of the precipitation. So we're just going to say that you're thinking that your soap detergent will produce the foam while your soapless detergents will not produce the foam when it mixed with water. Right, so that's very clear. And it could go the other way. You could say that the soapless one produces the foam and the soap one will not produce the foam. Right, because remember, it doesn't have to be a true statement. So that's your hypothesis. And then the required reagents from the list provided. All right, so we can, all right, so it says reagents. So we're not just going to use water alone. So we're going to use water, and you choose one. So we're using water and
Calcium carbonate.
So let's go with calcium carbonate. All right. And it's solid calcium carbonate, so we're just going to use the water to actually dissolve it to make it so it can react with your detergents. All right, so your method here would be that the first thing is to get your calcium carbonate to dissolve in the distilled water. So you're going to say we need to state how much distilled water we're using as well. So let's say we measure, let's use 50 centimeter cube. That's like a common 25, 50, that's like the normal amount of reagents that we normally use. So measure 50 cm cube of distilled water, and we're going to mix it with the copper carbonate in a beaker. Right? So that's our first thing, to get our copper or calcium carbonate in a liquid form. Now we have it in liquid form, then we can do what?
Add the soap.
So we're going to add, and it's a detergent, so it's a liquid form, so we can, let's say, use 15 cm cube. So to add 15 cm cube of let's use one of the brand. So the Mitzi Clean first. So we add that of the Mitzi, so the Mitzi Clean detergent into the beaker with the calcium carbonate. So after we do that, and then you tell them to mix it, then mix. Then finally you tell them what to actually observe. What would they observe here?
For the formation of foam.
Observe for the formation of foam. All right, and then our last method would be, we did it for one reagent type, so we're going to repeat steps 1, 2, 3 for the, let's see what the next detergent is, which is fresh always. For the fresh always detergent. And that's your method. All right, that's clear?
Yeah.
All right, great. And then our apparatus, again, we just identify the things that we used from our method provided there. So we measure 50 cm cube, so that means we use a measuring cylinder to measure that volume. We add distilled water.
Stirring rod.
We had a stirring rod. We also had the solid calcium carbonate. We had the beaker to mix it in. And then finally, we have our 2 detergents. All right, variables to be controlled. All right, let's go. So what are the control variables here?
The amount of
The volume.
water. Oh.
So the volume
Yeah.
of water, the volume of water. Next,
Volume of detergent.
volume of detergent. And there is another one that we didn't specify in our method, which is the amount of the CaCO3 used, calcium carbonate.
Yeah.
Right? So a key thing here is that even though for this question, you notice it didn't specify how much to choose, right? The safest
Yeah.
way to go is to actually identify all, right? But remember, it's never one. So once it says variables, you can't write one. The only way you're going to write one for an answer is if it states that give one of the control variables. Anything else, you give all if it doesn't state how much, or if it states 2 or 3, then you give the 2 or 3. All right, data to be collected.
Amount of foam formed.
So the presence of foam or the amount of foam. Right? Then discussion, which is what we have here. Right? So you state that when we have the reaction with the soap detergent, it would produce a foam with your calcium carbonate, and it will not produce a foam with your soapless detergent. Why do you think that's the case? Why do you think the soap detergent produces the foam and the soapless does not produce the foam? Anyone? Nobody? All right, so a hint is that it's actually stated in the aim. So the aim actually gives you the reason why.
Oh my God, one is an insoluble. Oh my God.
Right? So you see, everything sometimes is actually given to you. So it says that we're using ionic precipitation. And we should note that if we have a precipitation, then that means that it's insoluble. And if we don't have a precipitation, then that means it is soluble. Right? So that's the reason why there. So that's all you write. So remember, for discussion, you have to give at least one reason why you're saying your results would be of that form. All right, any questions for this one? Any questions?
No.
No questions?
Wait,
No.
what year paper is this?
January 2016.
Okay.
All right, so let's see. I think we did this one already with the vitamin C concentration. Yeah, I think we did this one. All right, so all right, this one is good. All right, so this one I'm giving you. So this one is no help from me, all help from you. So I'm not going to say anything because this is a topic that I discussed with you guys on the first lesson. So it should be easier for you to do this. So it says you're provided with a bottle of seawater, which also contains some salt. You're going to plan an experiment to recover the solid sea salt from the mixture. So we need the salt from our sea salt with the mixture of sea salt and sand. All right, so based on that, we know the drill. What's the first thing that we're going to do?
Make a solution.
What's the first thing when we read the problem?
Identify the topic.
Identify the topic. All right, and the topic here would be
Filtration, separating, yeah, separating.
separating techniques. And this one is easy because it tells you that we need this from a mixture. Right, so this one tells you exactly the topic. So separating techniques. Well, we know we have a lot of techniques here. So which one now would be for this problem?
Filtration and condensation.
So filtration and
Condensation.
condensation. No, not condensation.
Evaporation.
Evaporation. Yes, we can go with evaporation.
or crystallization.
or
Oh,
crystallization.
yeah, crystallization for real.
So evaporation or crystallization. All right, so those are the two techniques that we're going to use. All right, so we know the techniques, but we still need to drop down a little thing about each of these techniques. What do we know about filtration?
It's used to separate a solid from a mixture.
So it separates a solid from a mixture.
An insoluble from a liquid. I don't know to say.
Yeah, let's go with that one. That one is better. So for filtration, it separates an insoluble from a liquid. So you have to have something that's insoluble. And the next part is that the next part of the mixture has to be a liquid. Right? So if it's not a liquid, then we can't filter it. All right. So we know that about filtration. So what else do we know about filtration though? Nothing else that we remember?
What else is there to know?
All right, so when you filter something, which part goes through, which part remains?
Oh, filtrate goes through, precipitate remains.
Residue
So the
remains,
precipitate
yeah.
or the residue remains, right? And then the liquid goes through.
And the filters.
So the liquid, which is your filtrate, goes through. All right, so based on this problem, which one will stay, which one will go? So the residue. All right, so question, what would we be filtering? So I have the seawater and with the sand in it. What would we be filtering? That's the first thing that we need to know. What are we filtering? Mixed seawater and sand mixture. Great. So Isaiah says we're filtering the entire mixture. All right, so Isaiah told us that the mixture that we're filtering would be the sand with the seawater. So that's what we're filtering. So sand and the seawater. So out of this mixture, which one will be the residue?
The sand.
So the sand will remain, and therefore the filtrate would be the
Seawater.
The seawater. All right, so we know that, so that's our filtrate section. All right, so now let's look at the next part, which is your crystallization or evaporation section. So we need to know the crystallization. All right, so what do we know about crystallization?
It is used to obtain solid crystals from solution.
All right, so yeah, that's the same thing, and Isaiah says the same thing as well. So we gain the crystal, so we get crystal or salts from a solution. An important part of this part is, as Isaiah states, it's by heating it. Right? So same thing here. What are we going to heat in order to get the crystal?
The seawater.
So we're heating the seawater. And when we heat the seawater, what's going to happen?
The water will leave.
So the water will leave, and that leave is known as evaporation. So evaporate, the water evaporates, and then what happens?
Sea salt. salt.
Yeah, you can call it sea salt. So the sea salt
Remains.
will remain. And once you cool it, you get the crystals. All right, so we have all the information we need now from our two sections of the separating technique. So let's answer the questions. So the first part says a suggested list of apparatus to be used for recovering the solid sea salt from the sandy sea water. All right, so let's go. So let's identify the things that we're going to need.
Beakers.
So you need beaker,
Filter funnel.
you need a filter funnel.
Filter paper.
What's that?
Filter paper.
So you need a filter paper.
Crystallization bowl.
So you need your crystallization bowl.
Bunsen burner.
So you need your heating apparatus, which is your Bunsen burner,
Wire gauze.
your wire gauze,
Tripod.
and your tripod.
The solid
Anything?
sea. The sea water and sand.
And your mixture.
Mixture.
So a mixture of seawater and sand. All right, so that's all we need to outline the steps. So step one,
Make a solution.
well, you already will have the mixture, so you don't need to make it.
Oh, filter. Filter the solution.
All right, so let's write it like someone don't know how to carry out filtration. So you have to give the steps in terms of how do we do filtration.
Place a filter funnel into a beaker.
Place a filter funnel into a beaker.
With filter paper inside the filter funnel.
So let me help you out. So fold the filter paper. Fold the filter paper and place it inside the funnel. So inside the funnel, right? Then fold it over a beaker. Step two. Next,
Pour the into the filter paper.
so you're going to pour the mixture in the funnel with the paper, right? And just for conservation purposes, just to state that you collect the
Filtrate.
filtrate, right? So now after you collect the filtrate, we go to step three, which is,
Light the Bunsen burner.
right, so light the Bunsen burner. But you don't tell them to put the stand and the gauze and everything.
Yeah, set up the
So set,
tripod and the
right, so you can just say set up the Bunsen burner, the tripod stand, and gauze. Then you can say now, and light the Bunsen burner. Right? Then after you light the Bunsen burner, what will you do?
You place the filtration into the evaporation dish and place over the on the
So place
stand.
the content of the beaker in the crystalline bowl. I'll just call it the bowl here, a space, and place the bowl over the flame. And we can just final state,
collect crystals.
wait until, well, you can collect until, wait until the water evaporates. Then you collect the salt. Then collect salt. All right, so that would be your procedure for this one. It says a list of the main observations that would be expected at each stage of the experiment. And we already know, right? So all we would do is to write what we just wrote here for filtration. We write it here, and the same thing for crystallization. So we observe that the sand will remain in your filter funnel while the seawater will pass through into your beaker. And then for crystallization, the water will evaporate and leave back with the salt. Right, so that's what we would have for the observation. And then finally, a student suggests that solid sea salt contains chlorine ions. Outline a method to test for chlorine ions in the solid sea salt.
Litmus paper.
So litmus paper, what do you know about chlorine and litmus paper?
Turn a red litmus paper blue than white.
So it changes red litmus paper to blue, then white. All right, so all you do is so how would you do that? So you have the salt, so you dissolve the salt in water, in distilled water. Dissolve in distilled water. And then then place red litmus paper. Red litmus paper in the solution. Right, so that's how you would test with the chlorine with the litmus paper. Any other tests that you could use to distinguish chlorine?
Silver nitrate solution, I think.
Anyone? Any other tests that you could describe?
Adding just silver nitrate.
Great, and that one is better than this one. So I would probably go with the silver nitrate. So you can use silver nitrate and mix it with the sea salt, right? And when it's going to react, it's going to produce AgCl,
White.
right? And this gives you a
White precipitate.
A white precipitate. So this one is a better option, right? Because we know that the only chloride that is insoluble is silver chloride. So we definitely can say that sea salt has chlorine in it. Right, so that's a better option to use. All right, so are we clear with this question?
Yeah.
Yeah.
All right, so Isaiah is giving an option here. All right, so I'm going to wait a while to do this last one and then we come to this one. from Isaiah. I think this one is like a similar one to Isaiah. Let's see. You are provided with 3 colorless compounds: anhydrous calcium nitrate, anhydrous calcium carbonate, and calcium hydroxide, which are placed in unlabeled containers. You are required to plan an experiment using the action of heat to distinguish between these 3 compounds. All right, so the hypothesis: the compound anhydrous calcium nitrate, anhydrous calcium carbonate, and calcium hydroxide can be distinguished by application of heat. Why do you think they can be distinguished if we apply heat to them?
Because like 2 are anhydrous and 1 contains water crystallization. What else?
So what does anhydrous mean?
With water?
So it has water. It does. Anhydrous.
Wait, I'm not sure.
Is it?
Wait, without water?
Without water.
Okay. Oh, I was confused just now.
Right, and so if we apply heat, all right, so with calcium hydroxide, what will happen to calcium hydroxide if it is heated? Because that's the only one that does not have anhydrous in it.
If we apply heat to calcium hydroxide, then it will become anhydrous.
Sure.
Wait, if you add heat to calcium hydroxide, what?
Is so go again, Hank.
It will decompose and you will get oxide.
All right, so I only hear that it will decompose.
Yeah, and you get calcium oxide and water.
All right, so I heard that. So calcium hydroxide, if we heat it, it's going to produce calcium oxide and water. All right, so that's one thing that we know. And then let's look at the calcium nitrate. When we heat anhydrous calcium nitrate, what do you think will produce?
Nitrogen dioxide.
What's that?
Calcium oxide, nitrogen dioxide, and oxygen gas.
Great. So we get calcium oxide, nitrogen dioxide, and oxygen gas.
Yeah.
Right, and the last one is the anhydrous calcium carbonate. So we heat this. What do you think we are?
Carbon dioxide and calcium oxide.
And calcium oxide. All right. So you notice that each of these reactions have calcium oxide being produced. So we know we can't actually use calcium hydroxide to distinguish which one is which, right? Because all 3 reactions will produce this same compound. But we notice that the water is producing calcium hydroxide. So therefore, how do we know if the solute, if that compound is calcium oxide? If water is produced, right? So you'll see droplets of water,
Yeah.
right? So that one is simple to actually distinguish. How do we distinguish between calcium nitrate and calcium carbonate?
The
Oh,
gas they produce.
What's that?
The gas that evolves.
So the gas
yeah.
that is evolved, right? So the oxygen and the carbon dioxide. But how can you see the gas?
You can't. You can test for it.
So we can't see the gas. So how do we know that this one produces oxygen and this one produces carbon dioxide?
You have to
Okay.
test to distinguish between the two.
Yeah.
What's that?
Test to distinguish between them.
We have to distinguish. How can we distinguish between between oxygen and carbon dioxide?
Lime water and lighted spirit.
Exactly. So that means we have to call it the gas, carbon dioxide. We put it with lime water. And when it goes with lime water, it does what?
Forms a white precipitate.
It gives you a white cloud, basically, or a white precipitate, right? And then with the oxygen, we use
Glow splint.
It relies a glowing splint.
splint, and it gives it, relights it, basically, right?
Yeah.
So we
Yeah.
have all the information. All we need is to just put words to these to answer the questions. So the apparatus and materials needed. All right, so what are the things that we need? So the things that we need would be our compounds. So I have the CaOH, the CaNO3 bracket 2, and the CaCO3. Right, we need the Bunsen burner to heat. All right, we need your tripod stand and your wire gauze. All right, what else do we need? We need your,
Splint.
you can go to your evaporating dish or your crystalline dish or bowl, whatever you would say. All right, so those will get the crystals. But then we need to distinguish between the gases, so that means we need lime water
Gas syringe.
and the gas syringe. And we need our splint. All right, so with the evaporating bowl as well, you need a cover on one of them to show that water is present. So you need the cover for the evaporating bowl to show, well, it doesn't matter. So it doesn't matter there. All right, so your procedure. All right, so this one is long, so I'm not really going to write it. So we're just going to state what we're going to do. So the first thing that we'll do is to
Heat the.
yes. So I'll just write the summary of what you would say. So step one would be?
Set up the
Yeah. Set up the tripod, the Bunsen burner, and the gauze.
All right, so set up heating apparatus, and then?
place compound in evaporating bowl and then place it on the heat on the burner.
All right, so not bad, but one thing that's missing is you have to state the amount of your compound that you're using.
Oh.
Oh,
Alright, so because they're crystals, let's just measure the mass. So let's just use 15 grams. So 15 grams of, and we do one at a time. So let's go with, let's label them ABC. So I do 15 grams of each. And then we place A in the evaporating bowl with, all right, so we're going to eliminate evaporating bowl, and we're going to use a conical flask because gas will be evolved and we don't know when. So therefore we use the flask so we can put the syringe on the flask. All right, so the flask that looks like that. So at the
Okay.
top there, we put the syringe, right? So we put it in the flask with the syringe connected at the top. All right, then you heat it. So step 2, heat the flask and observe for any change. So one with any change in the syringe, any change in syringe volume. So if the gas produced, then the syringe will actually change its volume. So in syringe volume, or for water droplet. Right? And then you state that if the gas is produced, then we're going to do what? So if the syringe changed, then we're going to
Test for the gas produced.
test for the gas produced. So we test for the gas, and we know to test for the gas, we will put some through lime water. If we change to that, then it's carbon dioxide. We put some in the presence of a glowing splint. If it rekindles, then that means it is oxygen. All right, so that's what step 3 would be. And then step 4 would be that we repeat steps 1 to 3 for the sample B and C. All right, is that clear?
Yeah.
yeah.
All right. Next is state one precaution that should be taken in conducting this experiment. So one thing that would minimize any errors happening in this experiment.
Using the same mass of compound.
All right, so precaution is to ensure that all samples have the same masses. So the masses of all samples. I'd state the expected observations for this experiment in a fully labeled table.
Oh.
All right, so a table to show what we would expect is that we have our first column here, which would be our samples. Right, remember we labeled them A, B, and C. And then we have our first test was to heat. So observation. This column will be observations. We split up observation in terms of observation after heating, and observation with the splint, and observation with the lime water. So that's what our table would look at. All right, so if there was no gas produced, then the splint and lime water will not happen. So you have no observations there. If the gas is produced, then you have your observation when it is with the splint and when it is with the lime water. All right, that's clear?
Yes, sir.
All right. Finally, discuss the observations in the table. State clearly how they can be used to distinguish the three compounds. And this is what we did right here. And this is actually acceptable if you just have this right here. So you write your reactions when they're heated, and you show that the calcium hydroxide will produce water. So therefore, once you see water droplets, then that would distinguish to show that it's calcium hydroxide. The calcium nitrate will produce oxygen gas, while the calcium carbonate will produce carbon dioxide gas, which can be distinguished using the lime water and the splint test. So if it rekindles, then that means that it was calcium nitrate. If the lime water changed to a white cloud, then that means it would be calcium carbonate, and that's what you would have right there. All right, so it always helps to actually write down what you know about your topic before you start answering the questions, because it makes it easy for when you're answering the questions, you just look back at what you wrote down as your sample. All right, it makes it easy. And just a case, so let's say, unfortunately, the time is expired and you have this information on your paper, the CXC will actually use that as a part of your marking. All right, because this shows that you understand, right? And a part of your marking for CXC is your understanding. All right, we all clear?
Yeah.
All right, so the final thing that we're going to look at is the question that Isaiah posted. Let's just bring it up here. All right, so you're provided with samples of lead nitrate crystals and sodium chloride crystals. Plan and design an experiment to make lead chloride crystals. All right, so in this one is kind of simple, I think. Let's look. So we have lead nitrate, so PbNO3 bracket 2, and we have sodium chloride, right? And we need to produce one of the products that will be formed if we react both, which is lead chloride, and the next one produces sodium nitrate, which we're not concerned of. So we're not concerned of this, we just want to produce this salt right here. All right, so this, therefore, because PbCl2 is a salt, then that means the topic that this covers would be
Salt preparation.
the preparations of salt. All right, and we know that preparation of salt involves, first, if you need to prepare salts, you have to know to distinguish two things, that salts can be either soluble or insoluble. Right? So those two things will determine what type of preparation will be needed. So let's look. Our salt that we need to prepare is lead chloride. So we need to know, is lead chloride soluble or is lead chloride insoluble?
Insoluble.
So it's insoluble.
That's what I think. I'm not sure.
insoluble.
Anyone? Insoluble?
But
Are you saying that you think or you know?
I know that it's soluble in hot water though.
Yes, so you're actually right. Right? So lead chloride is actually insoluble. Right? So since we know that it's insoluble, then we now can determine what type of preparation we use for insoluble salts. What type of preparation is used to prepare insoluble salts?
Ionic precipitation.
Which is precipitation.
Yeah.
Right? Why is it called precipitation method? Because the precipitate is formed, right? So when you mix these two compounds together, you're going to get a precipitate form, and that precipitate will be lead chloride, right? But it also will produce sodium nitrate. So how would you get the lead chloride from your sodium nitrate?
Filter.
Yeah,
You will
filtration.
filter, all right? All right, so let's write it in the format so we can see. So the first thing we're going to do is to write a hypothesis for this problem. What can be a hypothesis?
To make lead chloride.
So that more would be like an aim.
Oh, oh my God.
So
Lead chloride is insoluble.
So lead chloride is insoluble, hence can be produced using
Ionic precipitation.
exactly by using your precipitation method. Right? Now let's look at the aim. That's where you can say what you are going to say.
To make lead chloride salt from lead nitrate and sodium chloride.
Exactly. So to produce or to make, or produce PbCl2 from PbNO3 bracket 2 and NaCl. All right. So let's hope we can finish in the time so we don't have to rejoin again. All right. So those are let's look at method before we look at our materials that we need. So the method, which we just stated, but let's just put it in step format. First step would be
to dissolve the two salts.
again.
To dissolve the two salts, the lead nitrate and the.
Great. So you're going to mix, and remember we always state how much we're using, right? So
Yeah.
let's mix 25 cm cube of PbNO3 bracket 2 and the same amount of NaCl solution in a beaker. After we mix, what we do?
Filter to remove the precipitate.
What's that?
Filter to remove the precipitate.
So once the precipitate is formed, Then filter off the product to obtain the PbCl2 in the filter funnel, because that's the part that will be the residue, right? So
Yeah.
so after that, another important part is that you're going to rinse your residue. What's the purpose of rinsing the residue?
For impurities.
Exactly. So to remove impurities. So you rinse the residue while it's in the filter funnel to actually
Filter out the water.
take out any impurities that would be with the salt. So after you rinse, your next step is to
Evaporate some or all of the water.
what's that?
Evaporate some or all of the water.
So you're going to evaporate any excess water. Any excess water from the salt, from the PbCl2. All right? And then that means that we allow it to cool. So allow it to cool to get the crystals. Right? And that's our method. All right, let's look at our apparatus. What are the things that are needed?
Beaker.
So we need our solutions. So the PbNO3 bracket 2. We need the NaCl solution. We mix it in a beaker, so we need beaker. We use distilled water to wash. We need filter
funnel.
and paper.
Do we need a stirring rod?
Can you repeat that?
Do we need a stirring rod?
A stirring rod? Yes, we do. So we need a stirring rod. We also need the Bunsen burner, tripod stand, and the wire gauze. So those are the things that we need. All right, then let's look at our variables. All right, and they only ask for control. So let's go with our control variable. What are our control variables?
The amount of salt.
Oh, there's one thing that Isaiah is adding here, you're evaporating both. All right, go ahead. What's our control variable?
The amount of solution.
So the volume of the Na, this should be NaCl, and the PbNO3 bracket 2. Any other thing that is controlled?
Isaiah said the heat, the amount of heat used.
All right, amount of heat. All right, so we can stick with that. And then let's look at our expected result. What do you expect to happen?
The electrobromide, the lead chloride.
The PbCl2 so this will be produced after the reaction. Will be produced after the reaction. Right? And that's basically what is expected, that you get. This will be produced after the reaction as a precipitate. As a precipitate. All right, let's add the discussion part. So for the discussion, what would you expect to discuss? Why would you have the precipitate?
Because it's insoluble, so...
Exactly. So Pb is insoluble, so it produces the precipitate, right?
Yeah.
And then also for the discussion, you state why you washed it, and why you wash it would be?
To remove impurities.
Exactly. All right, and then let's do one precaution. What would be a precaution?
Um,
All right, we have less than a minute. One precaution.
Overheating and burning the salt.
Exactly. So don't overheat to cause the salt to start it burn. Right? So ensure that the heating process is not too long. All right, and it's not too short. All right, so that's it, guys. All right, so I'll post this video so you can actually look back at it to see what you did not get on.
Okay, sir. Will we have another